slide. Let's take that slide and put it. Okay. pKa table. That's not even a whole pKa table. We had a nice. Where's our good pKa table? Sorry. Oh, I know where I had to find it. I had to go into their old examples. Okay. There we go. But, let us, oh no, I can't see. Oh no. There. So, H2SO4 is getting us to, HCl is starting to get us there. H2SO4 is getting us toward the range of the strength of the acid we need. And this is when these are not aqueous, right? Because if any of those strong acids are in water, then we're all the way up at negative 1.74, right? And we can't really have a stronger acid than that if we're in water, right? So these are going to be anhydrous. Okay. Bring me back my mouse. Okay. So, we protonate this guy. That's this guy. This guy is going to be a pKa of, is it on there? It might be. But I can't see. Looking for stronger acids, so we've got a protonated carbonyl. We do not have a protonated alcohol. And we're not going to look at this, right? We can't look at this alcohol and say this pKa is 16 and make that mean anything with this, right? Because that's for 16 describes how easy it is to take off this hydrogen. Now we added an additional hydrogen, so it's different. So this guy is somewhere around -2 to -3. So equilibrium. Okay. Now, that's just sort of, this is like a nice fun thing that happens. Okay, cool. I mean, that's gonna happen, some of that. But we've also got carbon, drawing the carbon. I'm gonna continuously forget to do that. All right, so let's take this guy, and we're going to be taking our nucleophile. This makes it a worse nucleophile, right? So there's gonna be some of this that happens. Luckily, chemistry is statistics, because there's so dang many. So dang many of each thing. So, they all smash together. So yes, there will be a lot of this, because we just added a strong acid. But there's still gonna be some of this, which is good, because we're looking for nucleophile, right? We just made our nucleophile worse. So luckily there's still some of this. And this is the part where we're going to talk about, this is the part where we're going to talk about how we decide what we're going to do, or how we fix acid reactions in an acidic environment. So if we do this, we end up with that. Can I do that? We're an acid. What did I do wrong? Yeah, we've got a negative charge. So, okay, that's fine. We just know we're probably going to do this, right? So when you're solving a problem, the biggest thing to get to is this, right? And last year I had a lot of confusion on how we know when we do this first step. So I'm starting here. Can I erase this side? Yes. Okay. So that is part of our problem solving process. Those are things that are going to happen. Well, this is something that's going to happen. This is probably what we're going to start with when we start trying to solve the problem. And we go, wait a minute. All right, fine, let's fix it. So, the first step, we go back, is we're gonna have that's a line. Well, okay, that's why they did that. Fine, we got rid of all of our really ridiculously strong acids, so we have some of these guys floating around. Because that's what we're going to protonate it from. So, now we've got this, right? Now we just made this into a much, much, much better electrophile. Yeah, it was green and now it's like extra super green. Now, we can do exactly what we just did, right? It's just that this looks like this, and so this ends up like this, and so we're okay. Yeah? So, to show you without just correcting that, we're going down. And we get this. Yes? Oh, I'm your way too. So, we get to this point. Let me get rid of this side so that's it's just really messy. I want it to be not so messy. I just don't have the ability, guys. We're gonna go, no, okay, we're gonna go this way. And we're just gonna go straight onto this board. That's how we're gonna do it. Okay, so now we've got this, and we're not entirely done, right? Because we haven't gotten ourselves to a hemiacetal yet. We're really close, but like one last step. And the last step is gonna be a nice simple, oh, that is not here, here we are. Okay, yeah, but why would I not do that? Okay, the slides where you actually have the mechanism are going to call this our tetrahedral carbonyl addition compound. I mean, okay, yes, I guess it used to be planar and now it's tetrahedral, but we've got 4 things bonded to it, so like, yeah, it kind of had to be that. And that's not like a proper name that anybody would, I don't know. Someone was trying to be like, oh, find me the tetrahedral carbonyl addition compound. I'd be like, is that a name of something? Okay, why? Okay, so that's dumb. Then we're just going to have some more of this, right? And we're gonna go, hey, what if instead of you having that proton, what if I took it instead? Thank you. And that's fast because it's acid base, and we get, yes?
Why does that get deprotonated instead of the alcohol?
Oh, so when we're talking about pKa's, you're talking about rather than here?
Yeah.
So pKa of an alcohol is around 16, right? So if you've just got a normal alcohol, that guy wants to be around 16. So let's draw this out. I'm gonna push this back so the camera can grab it, and we're gonna do it down here. Oh no, wait. The ugly side. Okay, we can do this. If we've got this pKa is 16-ish. Well, let's just do this and pretend this looks like this for now. If we've got this and we're putting that against this, let's just pretend they're on 2 different compounds for now. Yeah? Here. We don't need R's. R's are done. We can just have methyls. This guy's pKa isn't actually on our chart, right? But we talked about how it's a pKa of -2 to -3 generally, right? How can we know that if it's not actually on the pKa chart? Well, remember, strong acids are way down here, right? Down here, negative numbers. And this guy is an alcohol that has a full valence and no charge. This guy's an alcohol that has a full valence but has a positive charge. And we talked about how, okay, yeah, in general chemistry, we don't like electronegative atoms to have positive charges, but like in organic chemistry, all of a sudden we do that all the time, right? And that's mostly because we would rather have a bunch of full valence than deal with who gets the positive charge. Yes?
Is that why the lone pair on the oxygen on the left attacks the hydrogen, not the double bond? Because that would make it like a carbocation instead of
Yes.
the positive on the oxygen.
Yes,
Okay.
yeah, because if you attacked from here, you would end up with a charge separated guy here, and I mean, if you drew it that way, as long as right after drawing your products, you were like, oh shit, that's a carbocation, and you just drew more arrows, like, wait a minute, this negative, or this lone pair will come back down and form that, then you're not gonna lose a whole lot of points because you saw what the problem was. You may not have any, but like, my fingers turn black, and then I get like, under my nails, by the end of the day, like under my nails, there's black stuff under there, and then there's black stuff in my ears. Like, I didn't know this was a problem, but oh my goodness, and it's in my hair. It took me like days to figure out where, like why my scalp was just had black stuff in there. Sorry, ugh. So, when we're doing this, I guess we don't really even have to try to figure out, I don't know, I'm trying to draw this as an acid-base reaction, but like neither of these actually have to be the acid or base. So instead of drawing you a nice acid-base reaction where we have a pKa on this side and a pKa on this side, and whichever one's bigger helps us decide which one it goes to. We're gonna look at these, and basically pKa is how easy is that to take off, or how hard is it to take off. So this guy's -2 easy to take off, and that one's that's 116 easy to take off. Yeah?
Yeah, it makes sense.
Okay. I turned that into a really long explanation because I tried to do this thing, but that's because I was trying to turn one of them into a base and acid. And I was trying to do a reaction that wasn't actually happening. Sorry. But did that help? Make sense?
Yeah.
Yeah. So basically, once we get past all of the valent stuff, now we've finally started caring about electronegativity and the oxygen that doesn't really like the positive charge. Like, it's fine with it as long as everybody's got happy valence, a full valence octet. But if both of these have, these two, so these are going to be really similar. So we're going to do this, and we're going to go draw what we get. It's going to be this OH, O, that color, R, and that. We're going to get this. And we're going to end up with some of the pKa of this is probably -2 to -3 range, is the -2 to -3 range. pKa of this is probably also the -2 to -3 range. So like, this is one of those things where this is in equilibrium. We just do this step to show you we've completed this guy, right? Like, this is one of those, neither side is necessarily favored, right? But we're trying to show that we can make this in the end. So we have to show all the steps to get there. Does that make sense? So a lot of times we do like a protonation or a deprotonation at the end, and we're like, would that happen? Well, for some of it. And chemistry is a numbers game, so like, as long as some of it would do that, we're good. We have formed some of this, which means we can do something with that. Yeah? I know. Makes sense? We're okay. Okay. So, acid catalyzed is harder. Yes. But did that mess sort of make sense? Let me get more than one person not. This is yes and this is no. And this is help me. I don't want people behind me to see, but like help me. I don't understand. Okay, cool. Just making sure. It was so much easier when I could actually see, so I could see question face. So I used to be really good at identifying question face, but like, man, maybe I should get new glasses because 15-year-old glasses aren't overly useful. Okay. So, hemiacetals. Hold on, we're gonna do this slide and then we're gonna stop. Hemiacetals, once we make them, what can we do with them? Well, we can react them with alcohols to form an acetal and a molecule of water. So that's what our next thing's gonna do. We just did one step to form a hemiacetal, and then basically, if we do that, we can just keep going because we have a bunch more alcohol. Usually you're just gonna use your alcohol that you're adding as your substitute, or as your solvent, so that there's just like a ton of it that'll help kind of push that equilibrium. But yeah, basically that's, hemiacetal is sort of like the step one to the creating of an acetal. Okay. Now, we can take a